All right. So I want to thank everybody for being here today. I'm going to ask you to jump between two screens today. I'm going to ask you to jump between the Pear Deck screen, which I hope you're looking at now. The Pear Deck screen will allow you guys to answer some questions, sometimes right on the screen, and it'll also allow me to send you a copy of your answers when this is over. I, however, can't write on that screen. So I'm also going to ask you to jump back to the Zoom screen, and that will allow me to write on the screen and show you some stuff. So I want you to be able to see me working the problems. And the easiest way to do that is for me to go back to the main Zoom screen. If you're good with a computer and you have a big enough monitor, you could split your screen and have both up at the same time. That's not necessary though. I'll make sure that I tell you to either look at your Pear Deck window or your Zoom window. And just make sure you get used to that. Look at how to get between those two. All right, we're going to start in the Pear Deck window. Today, we're talking about forces. Last time, we talked about kinematics, which was the branch of the field of mechanics that talks about how things move, talks about motion, but it doesn't take into account the forces that cause that motion. Today, we're going to get into dynamics, and that's the branch of mechanics that looks at motion and the forces, or if we're rotating, the torques that cause that motion. So force is very simply any push or pull that can change the state of rest or the motion of an object. You guys know that in the SI system, what we usually call the metric system, we measure forces in newtons. And in our system, the English system, we measure them in pounds. We're going to use newtons, though, in this course almost exclusively. So hopefully you guys already know Newton's laws very well. We're not going to spend much time here with Newton's laws. The first law is sometimes called the law of inertia, a property of matter that it continues in its existing state of rest or motion unless it's acted on by some kind of net external force. Remember that mass is really just a measurement of something's inertia. We're going to use those two words almost interchangeably, mass and inertia. More mass means more inertia. More inertia means more mass. Newton's second law is probably the most important idea, at least in introductory physics. It's just net force equals ma. Really, really powerful. And it can kind of give us the definition of a unit. So if we think of force on the left, mass and acceleration on the right, mass we tend to measure in kilograms. Acceleration we usually measure in meters per second squared. So 1 Newton is 1 kilogram times a meter all over a second square. That's what a Newton is. That's important. And remember, Newton's second law is about net forces, forces that aren't canceled out by something else. Net forces cause acceleration. That will be the idea that we keep coming back to over and over and over again, and really over and over throughout all of AP Physics 1. Newton's third law, we're not going to deal with a lot today. It's the idea of the action reaction. For every action, there's an equal and opposite reaction. You can't push on something without being pushed back by that thing. Key idea, not as important in this unit, but very important throughout physics. So sometimes we talk about two different ways to look at mass. One of those ways is called inertial mass. So notice the bold words on here. I'm not going to try to read all this to you, but the bold statement under inertial mass. To determine an object's inertial mass, you apply force and you measure how much that object accelerates. So we know that in terms of Newton's second law, mass would be equal to force divided by acceleration. So it's one way to measure mass. A known force causes a certain amount of acceleration that allows us to calculate mass. Now we can also look at mass from a gravitational standpoint. And that really goes down to Newton's law of gravitation, which you see on the screen. F equals g m1 m2 over r squared. Gravitational mass is really measuring the mass by comparing the force of gravity on the object to the force of gravity on a known object. It's really how balances work. The idea, though, is that really inertial mass and gravitational mass are really two ways to measure the same thing. The two measurements should be equivalent. And this is the main reason why every object falls, accelerates at the same rate on Earth. So I'm not going to talk too much about mass versus weight right now, but I do want to talk about that equation, weight equals mg. So the weight of an object is its mass times the acceleration due to gravity. Mainly though, on this slide, I want to talk about contact forces. So contact forces are forces that have to be in physical contact with the object, as the name would imply. The main contact forces that we deal with in AP Physics 1 are the frictional force, the normal force, which you guys know is a surface pushing on an object, and also the applied force, when something is pulling directly or pushing directly on an object. So those three forces are the main types of contact forces we'll deal with. Now, in addition to contact forces, we also have non-contact forces. Lots of times these are called field forces. So gravity, we deal a lot with gravity in this class. In older versions of AP Physics 1, or what was called AP Physics B, we dealt with the other three of these, the electromagnetic force and the strong and weak nuclear forces. Those really aren't part of the curriculum anymore. So the gravity force is really the only non-contact force that you're going to be dealing with. But this is the force that can be applied over distance without direct contact. So key idea, you saw on that previous screen, net forces cause motion. When there's a net force, there's always acceleration. Crucial idea, the most important idea in AP Physics 1. Net forces always cause acceleration. That can be a change in speed, or it can be a change in direction. Either one causes acceleration. So another idea that we're going to get to here very quickly are what are called free body diagrams. Another really important idea in AP Physics 1. So these are used to show the magnitude and the direction of all the forces acting on an object. Now, something that's really important, the AP Physics 1 folks don't want you to break these forces into components and show those on a free body diagram. Very often to work a problem, you're going to need to break a force into components. You don't want to show those on your free body diagram. Don't show the components, just show the actual forces. Usually you show those with arrows. The length of the arrow should be proportional to the size of the force. So they are a really crucial tool in helping us work problems. They help us figure out where there's a net force. And I would say for most problems that you're going to do in this unit 2, it's a good idea to start with a free body diagram just to get an idea of what's going on. You will also sometimes hear these called force diagrams. So that's okay to call them either one. Most of the time in AP Physics 1, they call them free body diagrams. But if you see them called force diagrams, don't let that confuse you. So we've got two examples here. Or there's two ways we might draw them. One might be that we start off by drawing the object in question as just a dot, and we draw the forces coming out of that dot as arrows. And remember, the direction of the arrow is the direction of the force, and the size of the arrow is proportional to the size of the force. The other way is to draw the forces at the point on the object where that force is actually exerted. So we've got two examples. I'm going to show those to you on the next slide. So here we can see on the left picture, example 1, we think of the middle of that object as a dot. So we have a force of gravity acting down. We have a normal force acting opposite that force of gravity, up. We have a force of friction over toward the left. and we have a force applied, an applied force acting toward the right. All right, so those are all drawn from the center of the object or from a dot at that center. Example 2 shows the forces acting at the point on which they actually act in real life. So we have some kind of applied force pushing from left to right. That's the F there. We have weight acting downward on the object. We have a normal force pushing up on the object. And we have friction acting toward the left, right at where the box, in this case, meets the surface. In most cases, they're going to draw them like example 1 on the AP exam. Occasionally, you'll see an example 2 type of free body diagram. I prefer example 1, and most of the time when I draw them and have my students draw them, that's what they're going to do is example 1. All right, so I want you guys to, you should have a Pear Deck tool now. I want you to read the prompt, and I want you to draw the free body diagram that it asks you to draw here. So take about 2 minutes, read the prompt, and draw the free body diagram. Go ahead and get started now.
Can I have the code for the Pear Deck?
Yeah, so it's up in the upper right-hand corner of the screen, VLQWDR. VLQWDR. All right, looks like most of you have an answer. And so now I'm going to get out of Pear Deck for a second, and I'd like for you guys to go back over to your Zoom screen with me. And again, the reason I'm switching screens is so that I can draw on the screen and you can see it. So bear with me for just a second. I've got like 50 menus popping up on my screen here. All right, here we go. So we have a box on a horizontal surface. It's pulled with a horizontal force to the right. It accelerates. A frictional force acts on the object. Draw a free body diagram for the box. So let's just think of our box like so. So it's sitting on a horizontal surface. So first of all, I'm going to go to the middle here. And I'm going to draw an arrow that represents the weight of my object. I could draw that as a W for weight, or I could draw it as an F subscript G for force of gravity, which is what I'm going to do here. We know that because it's sitting on a surface and it's not accelerating vertically, that the force of gravity is being counteracted. There's an equal and opposite force that acts upward, and that's the normal force. And you could draw that as just N, or you could do it as force normal, like that. So vertically, I have no net force. Therefore, I have no vertical acceleration. Now it says that I'm pulling this object toward the right. So there's an applied force acting this way. I'll draw that as FA. It says there's also a frictional force though, but it does tell us that this thing accelerates. And let's assume it's accelerating to the right. If it's accelerating to the right, when I draw in friction, we know that friction always acts opposite of motion. So I'm going to draw friction like so, and I'm going to draw it as F sub F. And I make sure that this arrow is shorter than this arrow. And that tells me that there's a net force acting to the right. That's it. That's my free body diagram. But that lets me see that the only net force is a net force to the right. All right, now I want you to go back to Pear Deck. So this is, I'm not sure why I had this problem on here too. It's pretty much the same problem. So we're just going to skip over this one. That's the same thing. Let's look at this one. So we have a 20 kilogram box that slides down an inclined plane. Draw a free body diagram which depicts all the forces that act on the box. All right, so think about that one. All right, so let's go back. Let's see how many of you have answered so far.
It won't let us draw on this one.
Oh, is it not letting you draw?
No, sir.
Okay, well, let me just go back to my PowerPoint then. I'm not sure why it's not letting you draw on that one. All right, so let's draw an incline like so. All right, so here's my box. And first of all, I know that I have a force of gravity that always acts straight down. Now, normally when we're working a free body diagram or an incline problem, we would want to break that weight up into a component perpendicular to the surface, like so, and another component parallel to the surface, like so. But remember that we don't draw components on a free body diagram. So I'm just going to label this as F sub G for my weight. The other force, what are some other forces that are acting here, guys? Somebody unmute and tell me. What other forces should I show in this free body diagram?
Fn acts perpendicular to the incline.
Yep. So we got a normal force. Normal force always acts perpendicular to the surface. So I ought to draw it in maybe something like, well, that's a wavy line. That's supposed to be a straight line there, I promise, guys. That's the normal force. And then what else am I missing?
Is there friction?
There's friction. And which way should my friction arrow be going?
To the right.
To the right, kind of up and to the right, right? Because we know the box is sliding down, and we know that friction always acts opposite of motion. So that's what we're looking at right there. I see a problem that I skipped. I'm not sure what was going on there. So let's think about this setup. What do we call this kind of setup? It's really a popular kind of apparatus in AP Physics 1. What's that kind of machine called?
Is that a pulley?
Well, this is a pulley, but the whole setup with the table and the masses and the pulley, what's that whole thing called?
Was it an Atwood machine?
Yeah, it's called a modified Atwood machine. A basic Atwood machine is just a pulley with two masses hanging over it. So that's an Atwood machine. When you add in the horizontal surface like this one, it's a modified Atwood machine. And you're going to see all kinds of problems on the exam about Atwood machines like this or modified Atwood machines like that one. All right, is the screen letting you guys write on this one or not? Doesn't look like it. So let's just go ahead and I'm on the PowerPoint, no wonder. Let's just go ahead and look at this one and I'll draw this on the screen. So make sure you're looking at the Zoom screen. So we're wanting to draw a free body diagram for M1 and M2. So let's say that this is M1. You guys tell me what forces are acting on M1, box M1.
Tension force.
All right, I'm here. I heard a lot of just noise there. Somebody's mic's not working very well. Repeat one more time for me.
Force normal.
Okay, normal force, we know acts up, perpendicular to the surface. All right, what else?
Force
Gravity.
of gravity.
Think I heard gravity, weight. All right, what else?
Tension.
Tension. So the tension's the force in the rope, right? So that's going to be acting toward the right on box M1. And I could write that as FT or just T. I'm gonna write everything as F and with subscripts now. And then it doesn't mention it, but in the real world, what else is there going to be there?
Friction.
Friction. And we know friction always acts opposite of motion. So we'll draw friction going over toward the left, like so. So that's our free body diagram for M1. For M2, a little bit more simplistic. What do we have acting on M2?
Gravity.
Gravity. So FG. And what's the other force? You got
Tension.
some tension in the rope, right? And what do we know about that tension compared to the gravity?
The tension will be greater.
Okay, now, but look at the arrows here. Oh, I'm not sure why that arrow's the way it is. Typically, the way this Atwood machine is going to work is this thing is going to be let go and it's going to fall, right? I'm not sure why that arrow is looking like it's going up. Maybe that's showing you the direction of the tension. Point being, though, let's say that this box is moving downward and this box is moving over toward the right. If that's true, what has to be the relationship between the force of gravity and the tension?
Well, that gravity is greater than the tension.
Gravity's bigger. Now that's assuming it's accelerating. So let's say the object is accelerating. So that would mean that the force of tension is smaller but acting upward, while the force of gravity is bigger and acting downward. And we need to make sure that we draw this arrow a little bit longer than that arrow to show us that there's a net force acting on that object. All right, so let's get back to Pear Deck now. Let's go back to your Pear Deck screen. And I want you guys to look at problem 1 and go ahead and try to enter an answer for me. So go ahead and take about a minute, minute and a half. Try to work problem 1 and go ahead and enter your answer. Think about your free body diagrams as you're working this problem. Yeah, okay. We got about 4 more of you that need to put in an answer. I want to take a look and kind of show you guys what you guys are thinking right now. So here are the responses. So it's looking like most of you are saying either A or C. So we got lots of A's and quite a few C's. So now I'm going to go back to the PowerPoint screen so that I can write. And let's think about this. So we've got a force of 80 newtons being applied this way. There's no friction. If there's no friction, that 80 newtons is a net force, right? It's a net horizontal force. that net force is acting on what? What is that 80 newtons acting upon? That net force is the net force that acts on the whole system. The system in this case is made up of a 4 kilogram object and a 10 kilogram object, which means we have a total mass of 14 kilograms. I'm going to rearrange Newton's second law for acceleration. A equals F net over M. I'm going to take my net force of positive 80 newtons, and I'm going to divide that by the mass of the whole system, 14 kilograms. And when I do, I end up with about 5.71 or thereabouts. So my answer, best answer, A, which is what most of you got. The key there is that 80 newtons isn't just acting on box A, it's acting on the whole system because that's the net force for the whole system. Everybody okay with that? Those of you who said C, are you understanding why it's A? All right, let's jump back to the Pear Deck screen now. Here's problem 2. Same scenario, same boxes. Most everything about this problem is the same as 1, but it asks a slightly different question. So take a minute and try to answer question 2. Go ahead and input your answer. Remember that we found the acceleration in the last problem to be 5.71 meters per second square. You're going to need that to work out this problem. All right, I'm going to see what you guys are thinking. So I'm getting a lot of B's, a couple of D's, and 1 each of A and C. Most of you are saying B. Let's see if that's right. So I'm going to go back to my PowerPoint. So remember that we found the acceleration of the whole system to be 5.71 meters per second square. That's the acceleration of the whole thing. It's also the acceleration of each box, A and B. We want to know what force B applies on A. Well, first of all, I want to figure out what force A applies on B, because box A pushing on box B, that applies the net force acting on that box. Let's draw a free body diagram. So this is box B. So for box B, we have the force of gravity acting down. We have the normal force acting up. And the only force that we have acting is the force of A on B. So that force, the force of A on B, is the net force acting on that. So let's go back to Newton's second law. Let's calculate the net force that acts on box B. Well, the mass of box B is 10 kilograms. And the acceleration of box B is 5.71 meters per second square, which means the net force acting on that box is 57.1 newtons to the right. So that's the force of A on B. Now notice that's not what this question asks. This asks, what's the force of B on A? So this is where Newton's third law comes into play. If A pushes on B that way with a force of 57.1, then B also pushes back on A with an equal but opposite force, which means your correct answer here, most of you had it right, 57.1 newtons to the left. So that problem looks really simple, but you really had to apply Newton's second law and then Newton's third law to be able to get the problem. So you had to know quite a bit of physics to work that way. All right, let's go back to our Pear Deck. Problem 3, we really already answered. We found it first. What force does A apply on box B? So I think I already told you this, but just so you guys have the correct answer here is B. Go ahead and input B just so that you have the correct answer. If you go back and look at your Pear Deck takeaway, make sure you go ahead and put in B. All right, so problem 4, similar kind of thing. Go ahead and see if you can come up with an answer on this one. Think about a free body diagram for the parachutist, and that should help you. I'll give you another minute or two. I'm going to see what you guys are thinking. So most of you seem to be thinking D, but we got a couple C's, and we got one each of A and B. So I'm going to go back to my PowerPoint now. So I'm going to draw the parachutist here as just a box. This is my parachutist, and we have a drag force of 350 newtons acting on the parachutist. Well, you guys tell me, which direction is the drag force acting? Somebody unmute and tell me which direction I should draw that drag force in.
Up.
Yeah, well, it tells us, right? Drag, you can think of it almost like a type of friction. So I'm just going to draw it as FD. Now, some of you might have stopped there, and you might have thought, well, I should just go 350 divided by 50 to get the acceleration. But what force are we not? What force are we not showing that we should be showing?
Gravity.
What's the other force that needs to be in our free body diagram?
Gravity.
Yeah, the weight. And the weight would be the mass, 50, times the acceleration due to gravity. Weight equals mg. So our weight would be 500 newtons, 50 times 10 meters per second square. So we draw that a little bit longer than the drag force. So we have 500 newtons acting this way, and we have 350 newtons acting that way. So therefore, our net force is 150 newtons down. So D was the right answer. All right, let's switch back to Pear Deck. So again, same problem. This time it's just asking us for a different answer. Go ahead and input your answer for question 5. All right, I'm going to see what y'all are thinking. And most of you, almost all of you who've input are thinking A. So I'm going to go back to my PowerPoint. All right, somebody mute their microphone, please. So we figured out a second ago that we had a net force of 150 newtons down. That was our net force because of the weight being 500 newtons and the drag being 350 newtons. We know that net force acts on a mass of 50 kilograms. So let's just use Newton's second law. F net equals ma. A equals F net over m. So let's take that 150 newtons. I'm going to write it as negative 150 newtons since it's down. And I'm going to divide that by 50 kilograms. And I'm going to end up with an acceleration of -3 meters per second square, or 3 meters per second square down. So A was right. All right, I'm going to stop there for a second. Any questions on anything that we've looked at so far? Hopefully this is a review. Anybody have questions so far? All right, well, let's keep going then. So let's go back to our pair deck rather. And now I want you to go ahead and attempt question 6. And again, think about a free body diagram. All right, I'm going to see what you guys are thinking here. So most of you are thinking C. And let's go back to the PowerPoint now. And let's think about a free body diagram. So we had a rope and some kind of bucket. We'll just draw it like that. And it says the bucket is suspended from the rope and held without moving. How much tension is in the rope? Well, so let's draw a free body diagram. We know that we've got weight acting down. And remember, it's weight. It's not mass. Mass is not a force. So we've got to take that 10 kilograms and use weight equals mg. So our weight is going to be 100 newtons. Down, negative 100 newtons. And since this thing isn't moving, that means it's not accelerating. That means there has to be a force acting this way of equal but opposite magnitude. And that force is the tension force. So the tension force has to be positive 100 newtons. So our answer on this one should have been C, which is what most of you got. All right, so let's back up now and look at our pair deck. So here's our pair deck. So go ahead and attempt an answer on this one.
I didn't get a big lunch because the lunch meal wasn't a big lunch and I'm still hungry.
All right, so pretty much the same problem, but this time the thing is moving. So again, let's take a look to see what you guys are thinking. So it looks like an even split between B and C. And I can see that now C takes the lead. All right, so let's go back to my PowerPoint. And let's think about this. So again, the key is constant velocity. Well, constant velocity means what about acceleration? Somebody unmute and tell me. Constant velocity means what?
Zero acceleration.
Zero acceleration. What does that mean about net force? If there's no acceleration, what does that mean about net force?
There's none.
There is no net force. which means the free body diagram looks exactly the same in this problem as it did in the last one. We've got a force of gravity acting down. We know it's 100 newtons. We have a force of tension acting up. And we know that since there's no acceleration, that tension once again has to be 100 newtons. Remember, things can move without there being a net force. They just can't change how they are moving. They can't accelerate. Their velocity can't change. They can move at a constant velocity with no net force. It's just that velocity can't change. So the answer here should have been C, which is what most of you ended up changing to, I think, before we called the answer. All right, so let's go back to Pear Deck. Whoops. So, whoops, it wants to give you the answer here for some reason. Let's try again. All right, so let's try this one more time. Hopefully you guys didn't catch the answer there. Same basic problem, but this time the bucket is accelerating upward at 2 meters per second square. What's the tension in the rope? So take a minute and try to answer problem 8 for me. And again, think free body diagram. I promise it'll help you. So I'm going to see what you're thinking. A lot of you are thinking B. Several of you are thinking D. So let's go back to my PowerPoint. And again, let's go back to our good old free body diagram. So we know that we've got weight acting downward on this thing, Fg. And we know that weight is 100 newtons down, or negative 100. We know that we've got tension acting up. But this time this bucket is accelerating upward. That tells you, I hope, that the tension force has to be bigger than the gravity force because there's a net force in the upward direction. Now we know that when the object has no acceleration, we know the tension has to be 100 newtons for the bucket just to hang there. If the force of tension was less than 100, the bucket would fall. It would accelerate downward. So we know there's got to be at least 100. On top of that 100, just to hold it there, now there's a net force on top of that to accelerate it upward. And we're going to calculate that net force just by using F equals ma. So the mass of the bucket is 10. The acceleration is 2, which means the net force is 20. We know there's a net force of 20 newtons upward. Well, we know there's a downward force of 100 down. So for there to be a net force upward, there has to be 100 up just to cancel this out, and then 20 more up to give us that net force. So that's why our answer here is 120. 100 to cancel out the weight, plus 20 more upward to give us that net upward force. Does that make sense to everybody who didn't choose B? Anybody have questions why 120 is right here? All right, we've got about 3 or 4 more problems. Let's go back to Pear Deck. The last one I hope should be easy, the last one of this set. This looks, again, almost like the same problem, but notice this time the bucket is accelerating downward. So take a minute and input me an answer for this one. All right, let's see what you guys are thinking. So I'm seeing B's and D's, almost an even split. So let's go back to my PowerPoint again. And again, think about free body diagrams. So we know we've got weight acting downward. We know we've got tension upward. But in this case, the acceleration, there is acceleration and it's down, which tells me that this force of gravity has to be bigger than my force of tension. So I know that my force of gravity is 100 down, negative 100 newtons. I can calculate the net force that acts on the bucket using F equals ma. So I'll take the 10 kilograms mass times the negative 2 meters per second square, 2 meters per second squared down, to get a net force of negative 20 newtons. Well, I know I have a total of 100 newtons acting downward, but I only end up with a net of 20. So we could think of it almost like an equation. We could say the net force is equal to the force of gravity plus the tension force. We know that the net force is negative 20. We know that the force of gravity is negative 100 because it's down. Those negatives are important. So now we can solve for the force of tension and see that that force of tension is going to be 80. And if you draw it here, it's pretty easy to see that if you have 100 acting down and you have 80 acting up, you have a net of 20 down. I'm sorry, net of, what am I talking about? Yeah. So a net of 20 down. Therefore, the up force has to be 80 so that we end up with that net of 20. All right, let's go back to Pear Deck. All right, so here's a modified Atwood machine problem. And again, this is one of the most common types of problems on the AP exam. So take a minute and see if you can answer this one. A little bit more difficult than the last couple of problems, but not really if you know the trick. But again, think free body diagrams. All right, looks like you guys are struggling a bit with this, so I'm gonna look and see what the general feeling of the people who have answered so far is. So we're seeing 1A and 4 Bs. So let's go back to my PowerPoint. And let's think about this. So the key thing is, it tells us here that we're dealing with a frictionless surface and a frictionless pulley. So we got no friction. If we think about box 1 up here, if we free body diagram box 1 has a weight acting down on it. It's going to have normal force acting up on it. And it's going to have a tension force acting to the right on it. That tension force is the net force acting on it. That tension force And really, if you think of the whole system, it's really the best way to think of this is the whole system. In this case, what really is causing the net force on this system? What's causing this system to move, guys? Somebody help me out. What's causing the system to move?
The gravity,
Yeah, acting on what?
M2.
M2. So really, the weight of this box is the net force acting on the system. So you think of this as a whole system. Think of both objects. And so we're going to say F net of system is equal to mass of system times acceleration of system. So just take Newton's second law and think about the whole system. So I'm going to rearrange this for acceleration. So acceleration of the system is equal to the net force of the system divided by the mass of the system. And again, we said the net force on the system is the weight of this box, M2. So the weight of M2 is going to be 5 times gravity. So it's going to be 50. And we're going to divide that by the mass of the whole system. 10 kilograms for this mass, 5 for this one. So we're going to divide that by 15 kilograms system mass. And we end up, therefore, with about 3.33 meters per second squared down. Or we could say negative 3.33 if we're talking about this box. If we're talking about this box, it would be positive 3.33 because it's moving to the right. In this case, we're asking for the acceleration of the 5 kilogram box. It's going to be accelerating downward. So it will be 3.33 down or negative 3.33. Everybody okay with that?
How did you get the F net of the system again?
All right, so really the force that's making this system move is the weight of box M2. So I just took the mass of box M2 and multiplied it by G. So it's 5 kilograms times 10 meters per second square. Just found the weight of box M2.
Okay, thank you.
All right, so let's go back to Pear Deck. I think we have 2, maybe 3 more problems. Notice this one looks very similar. It's the same setup as the last one. This is another thing they're going to ask you is they're going to ask you about the tension. So see what you can do on problem 11. Remember that our acceleration was 3.33 meters per second squared for the system. You need that from the last problem. And then see if you can calculate the tension. Again, a free body diagram will help you. We'll see what you guys are thinking. So C is the big choice. B's got a couple of voters as well. So I'm going to go back to my PowerPoint here. And we could work this problem by thinking about either object. I'm going to think about just box M1 for right now. And I'm going to draw again a free body diagram for it. So I've got weight acting down, normal force acting up, and I've got tension force acting this way. This tension force, therefore, is my net force because it's the only unbalanced force acting on box M1. So it's the net force on box M1. So we can calculate the net force acting on box M1, and we can do that just by using Newton's second law. F net equals ma. The mass of box M1 is 10 kilograms, and the acceleration acting on that box, or was the acceleration of the box rather, was 3.33 meters per second square. And therefore the net force acting on that object is 33.3 newtons. Now we could also work that by finding the tension in this part of the rope. So let's think about it now in terms of the same problem in terms of box M2. So let's draw out a free body diagram for M2. So we know we've got a weight down, and we know we've got a tension up. We know this thing is accelerating downward, so we know the tension force is smaller than the gravity force. And we also could think about that the net force acting on this thing is the force of gravity plus the force of tension. We can calculate the net force acting on this object because we know that F net equals ma. And we know the mass of the object is 5. And we know that the acceleration was 3.33 meters per second square. For this object, it's negative 3.33, right? Because it's falling. So let's multiply 3.33 times 5. And that gives me a net force of negative 16.65. All right, that goes here. The force of gravity is going to be the force of gravity of acting on box M2, which is its weight. So that would be 5 times 10, 5 kilograms times 10 meters per second square. That's negative 50 newtons plus the force of tension. And then we just solve that out for the force of tension. So we're going to add 50 to both sides, essentially. And when we do, we get 33.35. So a little bit of a rounding issue, but 33.3 newtons. Does that make sense? Any questions on how I worked it either way there? Now, if you get into a little bit more advanced physics classes, you will see that these forces of tension are slightly different on each side of that pulley. Because that pulley, there's actually some friction acting between the rope and the pulley. But in AP Physics 1, we tend to oversimplify, and we do away with the force of friction here. So that simplifies things. But in the real world, these tensions would be slightly different because of friction. All right, let's go back to Pear Deck. And whoops, I'm giving you the answer there. This is the last problem for today. This is a regular Atwood machine. It's just 2 masses hanging over a pulley. You guys see if you can come up with an answer real quick. Hopefully you didn't see the right answer on the next slide before I showed it to you, or before I meant for you to see it. And again, free body diagrams will help. All right, I'm gonna see what you guys are thinking. So it looks like the biggest part of you are thinking D. So let's go back to PowerPoint real quick. So let's think about, let's just think about one of the boxes. I'm going to think about box M2. So we know that it's 60 kilograms, which means it has a weight of 600 rather newtons. And we know that that weight's pulling this way. We also know that the other mass is 20 kilograms or 200 newtons. And we know those two forces are pulling in opposite directions. So we have 600 pulling one way and we have 200 pulling the other way. Let's just think of it like this for right now. That I hope tells you that there's a net force acting on the system of about 400 newtons. That's the net force acting on the system. That net force acts on both pieces of the mass. So it acts on 60 kilograms and 20 kilograms. So if we want to find the acceleration of the system, let's just use Newton's second law. F net system divided by mass of system. So the net force acting on the system is 400 newtons. The mass of the system is 80 kilograms, and therefore the acceleration of the system, and therefore the acceleration of each box is 5 meters per second square. And since this specifically asks about box 1, which is the lighter box, it's going to be moving up. So answer D should have been our right answer here. If it had asked about box 2, the heavier box, then this would have been the correct answer. All right, so you saw on these Atwood machines, it's important to think about acceleration of the system, net force acting on the system, and mass of the system. So do Newton's second law in terms of system quantities first, and then you can find what you need to find. All right, any questions for me? All right, the problems today were mostly straightforward. Maybe the Atwood machine problems might have caused you some heartache or maybe some problems, heartburn maybe. But next week, same time, next Wednesday at 4, we're going to do some problems on inclines, which are a little bit more complicated. So if you felt good about today, that's great. Next time we'll get a little bit more complicated and we'll start looking at incline plane problems. Again, thank you guys for joining us. I'm going to end the Pear Deck session, and that should trigger you to get a Pear Deck takeaway here in just a few minutes. And that will appear under the shared with me section of your Google Drive account, whatever Google Drive account you use to log into this presentation.